Hello class, this is CSE-4600, Section 62, Week 15, Fall 2024. Okay, so this video is going to be one of two videos. So this video is going to be instructions on how to program your final assignment. So I originally wanted you to have this as a lab, but in the interest of time and for ease of grading, I've decided to have this be your final instead. So, that's it. This is video 1 of 2 for the last week of the course. The other video is just gonna be me talking about a few loose ends regarding operating systems. You don't have to watch it, but I would highly recommend you watch it anyway because, well, it just briefly talks about, I'll just briefly talk about the last bits of information regarding operating systems. Basically, a few more paging algorithms, I should say page replacement algorithms, and just a quick rundown of security and protection. So that way you have at least you'll have some more information going in when you finally take CSE-4610 one day. Okay, so this is your final project. We're going to make a sort of page fault simulator where we simulate the operation of a program. Now, this isn't going to be a perfect simulation, but I guess it's a good starting point anyway. So basically, we are going to generate a sequence of random-ish memory addresses that we're going to use. Then, what we're going to do is we're going to extract the page number out of those addresses, and then we're going to simulate loading a page into memory, and then as this program executes, it's going to generate new addresses that's going to correspond to new pages being accessed. If the program tries to access a page that isn't loaded into memory, that results in a page fault. That means the operating system must go into the backing store, which is usually a special area on the disk, load that missing page, select a page frame from which to load our page, in which to store our page, and then whatever contents was already in that frame are overwritten, and that frame is now used to hold the contents of our missing page. Okay. So we're gonna do this in several steps. So we're just gonna start off with a simple random number generator, because also let me just preface this first and say, when I say random in the context of random access memory, I should say, okay, better explanation. When a program runs and it generates these memory addresses, it isn't totally random, because if it were totally random, then caching would not work at all. We have CPUs that typically have 3 levels of cache, and the point of cache is, well, to load the most frequently accessed stuff so that the program doesn't have to, so that the CPU running this process doesn't need to go to memory to load that information. Of course, nothing will be in cache initially, so the first time the program tries to access something in memory, the cache is empty, and it's gonna have to spend the extra time needed to read something from memory. When that happens, a copy of whatever information it was accessing gets copied to the cache along with everything surrounding it. So if it's reading something from address 100, it's going to take the whole block of, like, say 100, address 101, 102, 103, 104, 105, and so on. It's probably going to copy a block of like 100 adjacent values I just made that up, but let's roll with it anyway. It's going to copy that whole block into cache. So that way, if the process needs to access that address again, there's a good chance it's going to need to access the next address after address 100. So that's why we copied the whole block. Basically, it's been observed that when programs access stuff in memory, there is some order in which the process accesses stuff in memory. This is called locality, and we take advantage of that so that when these programs run, they run just a little bit faster. The absence of caching, the worst that can do is slow down the program. And when you consider Moore's law not keeping up if we are using it as a metric for clock speed, which I've talked about Moore's law several times in the past, and basically, if Moore's law kept up as it did, then we should probably be in the terahertz range for clock speed, when these days we have just reached 5 gigahertz, and in the case of Intel's top of the line CPUs, 6 gigahertz! We've only just reached 6 gigahertz! The clock speed record for the longest time was 8 gigahertz, and then sometime in recent years, that record was broken, and it was, I believe it was like 9 gigahertz. No CPU is ever gonna reach that clock speed, because if it did, that computer is going to cook itself to death. Typically with overclocking records like that, the people overclocking the computer use typically liquid hydrogen, no, not liquid hydrogen, liquid nitrogen, and in some cases, liquid helium. And in some cases, like, entire refrigeration units. So, it is not practical for consumer CPUs to operate at such high clock speeds, because the cooling requirements for that is so astronomically high that it makes the computer prohibitively expensive. But then again, tell that to power users who can and do overclock their machines, but nowhere to the extent that these extreme overclockers do it. My point is, we need to make our computers faster, and we can't wait for we cannot. My point is, with Moore's law, we can no longer wait for computers to become faster by clock speed alone. That's why we started using pipelining to make computing faster. That's why we use other tricks to make computing faster, such as caching. And in cases where it's possible to do so, parallel programming. That's a class I teach. That's a class I used to teach that I started to teach again. But anyway, that's a whole nother story for a whole nother class. Okay, so let's begin with our random number generator. One problem. When we create this random number generator, it's going to create what's called a uniform distribution. That means if you think about it like rolling a 6-sided die, it's going to have the same probability of rolling a 1, 2, 3, 4, 5, or 6. That's not perfect. No, it is perfect, but it's not perfect for our purposes. Because, as I said, when programs generate memory addresses, there is an order to it. And more to the point, when a program runs and accesses pages, there is always going to be some set of pages that a program will access most frequently. My point is, we need to simulate that somehow. And I do have a lazy way of doing that, and it's as simple as rolling 2 dice. Check out this distribution here that I just pulled off the internet. When we roll one 6-sided die, there's basically a chance to roll a 1, 2, 3, 4, 5, or 6, and they're all the same. If we roll 2 6-sided die, then it becomes more interesting, because now there are more ways to roll a 7 than there are ways to roll a 1 or a 12. So we can use this distribution, this uneven distribution, to simulate what it would look like if this program that we're simulating, this uneven distribution, we're going to use that to simulate a program accessing certain pages more frequently than others. Okay, so we're going to begin with some code, and we're going to begin with a simple random number generator. If you're familiar with srand and time null, srand time null, yeah, we're going to use this random number generator. Even though C++, and I am going to be using C++ because there are a few data structures that I would like for us to use here. Even though the past few labs had us using a Unix machine and C and special libraries specific to Unix, with this lab, you're basically free to use any computer you want as long as you're able to compile and run C++ programs. And what if you don't want to use C++? Well, then you can just adapt these instructions. If you really wanted to, you can just adapt these instructions to any programming language you want. You don't have to be restricted to C++ if you're more familiar with a different language. As long as you're able to translate the code here into the programming language of your choice, you can do that too. Really, the point is, let's make this program. So we're gonna begin with a random number generator. So I have already opened up a Visual Studio project. Let's clear this out, and we're gonna begin with IOStream. That's for displaying our output. Let me zoom in so you have a really good view. So that way it's super duper clear. So maybe 175%? That's correct. Let's do it 200%. There we go. Nice and large, hopefully. Alright, IOStream, we need standard library.h and time.h. So now, C++ does have its own set of random number generators. They are called engines. This is just easier. Even though one of the engines is a bell curve distribution. If you know what a bell curve is, it's a very famous curve in statistics that looks like a bell. And the thing is, we can simulate that by rolling multiple dice. The more dice we roll, the more six-sided dice we roll. When it comes to the frequency of values coming up, the more and more it starts to look like a bell curve, which is a really interesting phenomenon in statistics as well. But moving on. Let's just make a random number generator. And let's write the skeleton of our code. srand time null, that is our random number generator. It's going to use the system time as a seed. You probably know this by now, but if you don't, bear with me here. Basically, with most of these, with random number generators like this, they aren't totally random. You need to get them started using a special value called a seed. That makes them deterministic. That means if we know the seed, then we can figure out ahead of time what the random numbers are going to be. Which is good for some situations, such as Minecraft seeds, where if you load a Minecraft world and has some really cool terrain generation, you can just save the seed, share them to a friend, and then they can generate the same world block for block. Unless they're on a different version of Minecraft, because the Minecraft terrain generation has changed like 5 or 6 times already, I think. Anyway, Because we need an input value, this makes our random number generator pseudo-random is the term here. Don't worry about it. It's good enough for our purposes, so we're just going to proceed anyway. We're going to generate 20 random addresses. And then we're just going to print each one by one. So, because you're probably familiar with working with a random number generator like this and typing something like rand modulo. We're gonna do 10,000 here, and then there will be a +1. Don't do the +1. We want our addresses to start counting from 0, and with modular arithmetic, it's gonna start from 0. Okay, so now with this line, we are generating a random address from 0 to 9999. That is a uniform distribution, which is, well, not what we want. But instead, what we want is this. Check this out. I'm going to add another random value to it. So, rand address plus equals the right-hand side of the previous line. So, this is just like our 2 dice rolls. So, if you roll 1 6-sided die, it's going to have a 1, 2, 3, 4, 5, or 6, but the probability of any one of them is the same. With 2 dice rolls, with the 2 dice being rolled at once, there's going to be a 2, 3, 4, 5, 6, 7, 8, 9, 10, or 11, but the most common value you'll get is 7 or something in the middle of that. So that's how we get our dice rolls here. By doing this, we're gonna have addresses around address 10,000 appear more often than any other address. And although I'm not gonna do this here, we can make this more pronounced if we just added this. If we just added random address plus equals rand modulus 10,000 2 more times. However, that's going to change the range of our addresses from 0 to 39999, which is what we do not want. If you wanted to do this, you just have to divide the result by 2. So yeah, if you wanted to do this, make it even more likely that the program will access pages 10 and 11, you would need to divide it by 2, because every time we add another random value, it's going to change the maximum value from, well, with this one here, it's going to be a max value of 10,000, and then 20,000, and then 30,000, and then 40,000. If you wanted to add this twice more, you have to divide the result by 2. Do that if you want to, but I'm just gonna leave it at this for now. That way, when we add these 2 random values together, we have an address that ranges from 0 to 19999. 19999? Shouldn't we be using base 2? Well, we can, but I think for ease of understanding, we're just gonna pretend that this is the addresses for a theoretical decimal computer. So, what that means is, the upper 2 digits of our address is going to correspond to a page number. And then the lower 3 digits corresponds to an offset. What makes base 10 interesting for this is the fact that if you just want to look at the first upper 2 digits, because everything is divisible by 10, we can just divide that value by 1000. And if you want the offset, you just do modulus 1000. And through that alone, we can extract the page number and the offset. And base 10 is not unique with this. You can do the same thing with base 2. I'm just starting off with base 10 just to give you an intuition of what's going on, especially if you're not familiar with your powers of 2. 1, 2, 4, 8, 16, 32, 64, 128, 256, 512, 1024, 2048, 4096, 8192, 16384, 32768, 65536, 131072, 262144. I don't know what comes after that, but I do know it's 1048576. That is 2 to the 20th power. 167777216 is 2 to the 24th power. 214748368 is 2 to the 31st power. And that's as far as I know. Sorry. I'm sorry about that. It's just... Eventually you're going to have to memorize the powers of 2 if you haven't already. At least go as far as the 16th power of 2. Anyway, moving on. We got a random number, and we want to print it out. Okay, now let's run it. I'm gonna press Control F5, and it's going to build the program and then run it. And now we have a sequence of 20 random addresses. So we can just, because this is base 10, we can just eyeball the addresses and just infer the page numbers that way. So we have pages 15, 11, 9, 9, 4, 10, 12, 9, 10, 5, 11, 9, 9, 9, 10, 15, 5, 16, 3, and 4. So that is a random sequence of addresses that we're going to use for our page fault simulator. Okay. Let's modify this program further. So instead of printing out the entire address, we're just going to extract the page number from it. So this is as simple as integer division. So that is as simple as integer division. So int page number equals random address divided by 1000. This is integer division, so there is no denominator or floating point anything. I'm gonna copy this, paste that here, and then I'm gonna add to this C outline. Process is actually accessing the following page. And now we're going to see what page numbers those are. Okay, so because this is a random number generator, the sequence of pages, and by extension the sequence of addresses, is going to be different each time. So now we have the pages. So pages 8, 12, 13, 7, 7 again, 12, 15, 7, 6, 8, 10, 7, 14, 14 again, 6, 16, 11, 8, 7, 4. Okay, now we have a random sequence of addresses. At this point, we have completed part 0. Run this program, and now I have page numbers 10, 12, 4, 15, 14, 17, so on and so forth. Take a screenshot of that, and that's going to be part of your lab report. Now we move on to part 1. We are going to implement the first paging algorithm, the first page replacement algorithm. Okay, hold on. Before I begin, I must address the elephant in the room. I forgot a line of code in the instructions. So, what you need to put up here is this. Include list. Because the next thing we're going to do is we're going to create a list of integers, an integer list that's going to be used for our FIFO queue. So let's add that in now. Okay, so we need to add this line here, include list, because we need that data structure for this. There we go. Oh yeah, we need an integer for this one here. FIFO page fault count, we're gonna set that value to 0. Alright. Now that we have our FIFO queue, we need to add another line of code here, and that is going to be how many page frames are we using this program in? Let's do this. Okay, so when we run this program, we're going to run it with 5 page frames. Which means that we have this sequence of pages that we're accessing, but there's only going to be enough room for 5 of those pages. We can only load 5 pages at a time. Which means as we progress through this program, we must unload and load new pages as needed. And the simplest way we're going to do that is with first in, first out page replacement. As a reminder, we talked about this in a previous video, along with 2 other page replacement algorithms. One of them is called optimal page replacement, which we can't really do with this setup. Well, we can, but we need to generate the addresses ahead of time, and even then, it's only good for benchmarking. The other one is called least recently used, but that's gonna come up in a few parts later. So, we're going to now implement FIFO page replacement. We need a little bit of knowledge of how this data structure works here. So, the first thing we need to do is check whether... Okay, so this queue is going to be holding page numbers. That's going to be a stand-in for actual pages being loaded into memory. We need to check this queue to see whether the page we have was already loaded into memory. And the way we check that is with this one following line of code. So, I'm going to put it right after this line. And let me just add some comments here. So we're going to be needing an iterator for this. So I'm just going to type in auto iterator, or maybe iter, equals standard find FIFO queue dot begin FIFO queue dot end page number. So basically what this does is iter is going to be some pointer that points to a node in this list. What find is going to do is it's going to search the whole list to see whether the page number we have was in that list. If it is, then it's going to point the some node in that list. If that node, if none of the nodes contains the page number we're looking for, then that iterator is going to point at the end. If that is the case, that means we did not find our page number. That also means we need to load our missing page into memory. Okay. Okay, so to reiterate, we performed this find procedure to see if the page we're looking for was already in the queue. If it is, then the value of iter should not be equal to FIFO queue.end. If it is, that means the page we were looking for was not in the queue. That means we have to push it to the front of the queue. If the queue is full, then we need to pop from the back of the queue. That's because we have a 5-page limit that must be upheld at all times. Okay, let's code that now. If iter equals if iter does equal the end of the queue, that means we did not find our page number. In that case, I'm just gonna write in a line of code here. Okay, so that results in a page fault, so now we have to simulate adding in the missing page. We're going to do that by pushing the current page number here into the front of our queue. So Now one thing we could do is perform this pop operation before we push. I'm just gonna do it the other way around because that's how I have it written in the instructions. Basically, we're just gonna push and then do a pop. So if FIFO.size is less than number of page frames, then all I gotta do is pop the page that's at the back of the queue. And that's it. So now when we run this program, now we can just eyeball the number of page faults that we got just by looking at the output. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay, 14 14 page faults from 20 page accesses, we won't know whether that's good though. We won't know whether that's good or bad until we start performing more tests. Oh, by the way, the auto keyword here, when you use this in an assignment operation, when you use this on a line like this, basically what it does is it tells the compiler, okay, whatever data type this is, figure out yourself, and the compiler is smart enough to figure that out. If, in case, your compiler does not know what the auto keyword is, just replace the auto keyword with this instead. Standard list int iterator. Since Visual Studio knows what auto is, I'm just going to use that instead. Okay. We're almost done. All you gotta do now is add in code that will increment our FIFO page fault count by 1 every time we get a page fault. So, let's do this. FIFO page fault count plus plus, and then we just have to add an extra line of code after that for loop that looks like this. So instead of just eyeballing it from the console output, we can just read it at the end of the thing. 16 page faults. Still, we don't know if that's good or bad. Alright, so now we have FIFO page replacement working. Now, what I want you to do is run this, take a screenshot of it, because we're gonna need this page sequence for a later step. So this sequence of pages generated, write that down, because we're gonna test it out with a different page replacement algorithm later. Okay, we're gonna close our consoles here, so that way it doesn't clutter up my workspace. And we're going to continue on with the next step, and that is to implement LRU page replacement. So LRU page replacement is a bit more involved. I talked about this in class as well. But before we begin, we're just gonna comment out this line here and this line here, because it's about to get annoying at this point. And especially all we really care about is this line here. Actually, maybe we don't need to comment out this line here after all, simply because we just want the page. No, we still want the page numbers, so do not comment out this line, but you may want to comment out this line. Okay. Here's where things get interesting. First, I'm just gonna copy this and paste it down here. This is going to become our LRU stack. As I mentioned earlier, in the earlier video, this isn't really a stack, it's actually a linked list that we're pretending is a stack. So this is going to become our LRU stack. And then I'm going to change this, so it's now our LRU page fault count. You see where this is going now? We are generating a list of addresses and seeing whether we get page faults. Okay. Let's try it again. Let's try this again, see if anything broke. Okay. It's still working the same as before. But at the end, let's just get ready for our output, and that is going to be our LRU page faults. There we go. So it should print as 0 because we didn't increment it at all. Okay, so now it's working. We just need to add in the code that will actually increment the LRU page faults. For that, we need our stack set up to simulate LRU page replacement. As I mentioned, LRU page replacement has a very high computation cost. And for that reason, not many systems implement true LRU. I'm gonna explain it more in the bonus video, but basically, there are a few tricks to simulate true LRU. So let's just close this for now, and we're gonna try pure LRU. I'm gonna add some separators here, so. So first is that. And now we have that. I'm also gonna close, I'm gonna also minimize this code so it's not in the way. So there we go. All our FIFA code is done now, it's working. Now, let's get to work on programming least recently used page replacement. I'm going to begin by copying this whole line again, because it is the same data structure we're working with. So we're going to look into our LRU stack to see whether the page we need is already in there. If it is not in there, then this iterator will be pointing at the end of the stack, if you will. And if that's the case, then we need to add that missing page to our stack. And even if it is there, we still need to do extra steps. You'll see. Let me just adjust this code. So now we have iterator and iterator 2. It's not our FIFA queue, but now our LRU stack. So, and the base number stays the same. There we go. Let me just add the skeleton of the code here. If iter2 equals, or I should say, does not equal if the page we're looking for is in the stack, then this iterator will not be pointing at the end of the stack. If that is the case, we need to move that page to the top of the stack. Okay, so now we have two situations that could happen. The page is in the stack, so we need to move it to the top. Or the page is not in the stack, and we need to add it to the top. And if that stack is full, we need to pop whatever page is at the bottom of the stack. Let's code that in now. So there are two ways we can do this. We can use the iterator and just move the node to the top, or we can do it a lazy but potentially inefficient way where we're just gonna erase that node from our stack and just re-add that page number to the top. I feel like that's a little bit easier to program, even though it might be a little bit more efficient because we just destroyed a node just to make a new version of that node. Okay, so lru.stack.erase, and we're just gonna pass in iterator 2, because that has the address of the node that contains our page number. So all I gotta do is pass in that, and that already deletes the value from our stack. So we can put it on the top again. There we go. Done. So if the page is not at the stack, all you gotta do is this. And if that stack was already full, if that's the case, then the code would look something like this. There we go. Okay, but we're almost done. If the page was not in the stack already, that means we had a page fault. So I'm going to increment page fault count as follows. There we go. So now if you run this program now, we should get a page fault count for both FIFO and LRU. So now it works. I guess another question is, those two page fault counts are the same. Is there gonna be a case where they're gonna be different? Let's try it out. Oh yeah, there was. I don't know if you saw that, but that was an 11 and a 12. 19 and 19, 13 and 13, 17 and 16. So yes, it does result in different page fault counts. Can we go back to our random number generator to make this access certain pages more frequently, more pronounced? And as I said, we can if we do this. I'm gonna do this, and then basically this makes it more likely that the simulated program is going to access pages 10 and 11 more frequently than pages 0 and 19. Let's try it again and see what we get now. 11 and 12. 13 and 14, 15 and 15. Sometimes we do get high page fault counts and low page fault counts, but that's just the nature of the random number generator. Sometimes we get FIFO and LRU page fault counts that are the same. 12 and 12, 12 and 13, 15 and 15, 16 and 16, 13 and 13. It really depends on the sequence of pages being generated. So, for one of these runs, take a screenshot of this, and then record the page fault, and then record the page fault count for this. So we previously got a page fault count for FIFO page replacement, and now we have one for LRU. We're going to take those two strings, and I want you to now manually perform optimal page replacement on it. So, I'm going to walk you through this with one of these strings. So, what I'm going to do is I'm going to pause the video here so I can record this sequence of strings. Sequence of page numbers. Since I already know that the page fault count for this using FIFO and LRU is 15 and 15, really what I want is one where the page fault counts for the two are different. Here we go. This'll do. So, I'm going to record these. I'm going to record this and see if we get a much better... we're going to see whether this resulted in a better page fault count if we use optimal page replacement. What that would suggest is if optimal page replacement yielded a lower page fault count, then that means there's something about this that is inefficient. And really that's to be expected because optimal page replacement, because we don't have the luxury of a crystal ball as being computer hardware, we don't know ahead of time how our programs are going to behave. So even if optimal page replacement yielded better results, it's not like we can actually implement optimal page replacement anyway. Really, we just use it for benchmarking purposes. So I'm gonna pause the video so we can work through optimal page replacement together as an example. Okay, now I am in Excel and I've transcribed our sequence of page numbers. So we have 5 page frames that I'm just gonna mark as follows. So let me just move that, and there we go. We have our 5 page frames. So let's try it out. We are at the beginning of our program and we are trying to access page 5. But we began our program with none of the pages loaded. This is called demand paging, and no pages will be loaded unless it is demanded by the program. Because we have no pages loaded, we have 1 page fault right off the bat. Okay, so that's the first one. I'm going to mark page faults with this orange color here. We know that page 6 isn't loaded either, so that's gonna become another page fault here. So that's another page fault there. Maybe it'd be easier if I just did this. Okay, so I'm just gonna do it like this instead. Okay, page 12 is not loaded into memory, so yeah, that's going to be a page fault. Page 7 is not loaded into memory, so yeah, that's going to be a page fault. Page 16 is not loaded into memory, so yeah, that's going to be a page fault. Okay, so here's where it gets interesting. Now we need to load page 9, and it's not loaded into memory. Which of these pages are we not going to be using for... Okay, so let's look at these pages. We need to load page 9 in here, but we don't have room for page 9. So we need to remove one of these pages. So which of them are we going to remove? Well, let's look at page 16. Are we going to be using page 16 ever again? No! No, we're not! Okay, so we already know that page 16 is already a good candidate for page replacement. So I'm just gonna mark that as green just in case. Let's look at the other candidates. Do we need page 7 again? Yes, we do. Do we need page 12 again? No, we don't! No, we don't! So really, now we have a tie for which page to replace. Okay, do we need page 6 again? Yes, we do. Do we need page 5 again? Yes, we do. Okay, so because we have 2 options for which page we need to replace, let's go to the first one and replace page 16. So now we have our stack that looks like this. I'm gonna clear the formats for that one, and now we have page 9. So this resulted in a page fault. Yes, 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 and yes. Okay, so now we need to load page 4. We already know page 12. We already know that page 12 won't be loaded ever again. So now we have a freebie. Page 4. We need to load that, so we may as well load it. We're gonna load page 4 in the place of page 12. So I'll put page 4 here. And I'll just copy all our other pages here. So yes, we got another page fault. We are accessing page 7 now. Do we have page 7? Yes, we do. So I'm just gonna copy that, and no page fault this time. Okay, page 11. So of these pages that we have, which of them are we not going to use again? Okay, so let's check this out. We need to load page 11. Do we need page 9 again? Yes, we do. Do we need page 7 again? Yes, we do. Do we need page 4 again? No, we don't! So I'm just going to mark that with a green. Do we need page 6 again? Yes, we do. Do we need page 5 again? Yes, we do. So what I'm going to do is I'm going to replace page 4 with page 11. And that's another page fault. Okay, page 17. We need to load page 17 now. So, do we need page 9 again? Yes, we do. Do we need page 7 again? Yes, we do. Do we need page 11 again? No, we don't. So that page is a good candidate for replacement, but okay, we already know that page 6 and 5 we do need still. So we're going to then replace page 11 with page 17. And I'm just going to copy the other 4 pages this way. So that was another page fault. Okay, now we need page 10. Page 10. We need to load that. But of these pages that we have, which of these do we not need yet? Or which of them do we not need at all? Do we need page 9 still? Yes, we do. In like 4 steps. Page 7? Yes, we do. Like 2 steps later. Page 17? We don't need it again. We won't need page 17 ever again. We still need pages 6 and 5. Those can stay. So, page 17, we'll put page 10 in its place. Copy, paste, copy, paste. Okay. So now we have pages 9, 7, 10, 6, and 5 loaded into memory. That was another page fault, by the way. So, page 6. Do we have that in memory? Yes, we do. So I'll just copy, paste that, and no page fault that time. Do we need page 7? We have page 7. Do we have page 7 loaded? Yes, we do. So I'm just going to copy, paste that. Do we have page 5 already? Yes, we do. So I'm just going to copy, paste that. Do I have page 9 already? Yes, we do. So I'm just going to copy, paste that. Oops. We already have page 6. We already have page 6, page 5, page 10, and page 10. Okay, how many page faults was that? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we had 10 page faults using optimal page replacement. That is, we replace the page that won't be used for the longest amount of time. Even better, if the page will not be used ever again. And coincidentally, we got a lot of pages that were only used like 1 or 2 times and then never again. So with that, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 page faults in comparison to the 13 and 14 that we got with FIFO and LRU. So in this example, we got 14 page faults with FIFO and 13 page faults with LRU, but then 10 page faults with OPT. Which means that OPT beat the 2 of them, but not by much. And even then, LRU and FIFO were pretty close. So yeah, you're gonna be doing this twice. First, with the string that you got in part 1, though you're just gonna be comparing the performance of FIFO versus LRU. And then once again in part 2, where you compare the performance of FIFO, LRU, and OPT together. I'm gonna need to update these instructions, by the way, so. Oh yeah, you may also want to use an online tool to verify your results. Let me just update these instructions as well. So really the question that you're answering is, did you get a lower page fault count using OPT? Oh, and by the way, you're doing this twice. First, with the screenshot from part 1, where you're just comparing FIFO versus OPT. And again, in part 2, with the screenshot taken there, where you're comparing FIFO, LRU, and OPT. Really the point is to get you practicing with finding out page fault rate manually. Not that you'll ever need to do this, but it is good practice after all. Okay, so let me just amend some instructions and I'll be right back. Okay, so to reiterate, part 0 was just to make the random number generator. Part 1 is implementing FIFO. I've updated the instructions, so you should see updated instructions on Canvas sometime tonight. Part 2 was implementing LRU. Part 3 was benchmarking those two against optimal page replacement and seeing whether OPT got better results. There's a good chance that it might, though. Part 4 is we're going to benchmark one of our strings. So the string that we got from this, we're going to copy that, and then we're going to see what happens when we start with one page frame, and then just increase the page fault rate increase the number of page frames one frame at a time. So what I'm going to do is I'm going to add another data structure here. And then, since I already have Excel open, I'm just going to copy this whole line and put it here. So I'm gonna add some comma, chameleon, and then I should have these page numbers all in a neat vector. There we go. So now we have an array hard-coded, a hard-coded array for our page numbers. Now, you can do this with either the sequence you got from part 1 or part 2. So, we're going to see what happens when we use the same string, because we're going to benchmark one string now, one sequence of page numbers, instead of having it be random every time we run the program. Okay? We need to do a few changes here. We're not going to be using the random number generator again. Instead, we're not going to get the page number from the address. We're going to get the page number from our vector up top here. So there we go. So now we have our page number sequence. So if we run this program now, it's such a simple change, but now we should be getting the same result every time, simply because we just hard-coded the dang thing. Okay. So this is part 4 of your instructions now. Modify your code so that it has an array of page numbers. You can use you may use one of the sequence of page numbers that you used for part 3. So your code should look something like this, which is what I have here. And now, what we're going to do is this. We're going to change the number of page frames to 1, and we're going to run our program. We got 18 page faults there. We got 18 page faults. That is higher than what we got when we performed OPT. And that was with one page frame. So we're just gonna compare performance of OPT, not OPT. We've already compared OPT and we already did OPT versus LRU versus FIFO. Now we're doing FIFO versus LRU with different page frame counts. Okay. So let's make another table. So we have 1, 2, we're gonna slowly increase our page frame count from 1 to 20. So we know with one page frame, which is what this is here, we got 18 page faults each. Okay, let's just populate our table as such. 18, 18. So we have 18 page faults for both FIFO and LRU. Let's do this again with the maximum number. Let's do this again with 20 page frames. The string of the sequence of addresses will have up to 20 unique page numbers, even though we're probably not going to be accessing all 20 pages. But this program is set up so we generate a sequence of 20 page numbers. So I'm going to run this with 20 page frames. And now we have 10 and 10 page faults. Okay, that means with 20 page frames, we have 10 and 10. We have 10 and 10 page faults. With 20 page frames, we got 10 page faults for both FIFO and LRU. So let's go back to the beginning, and we had initially set this. We were starting with one page frame, and we got 18 page faults. So let's do this again with 2 page frames, and we get 18 and 18 page faults. I'm gonna put these side by side for convenience sake. And there we go. Let's do it with 3 page frames now, and we get 17 and 17 page faults. If we do this with 4 page frames, we get 15 and 15. If we try it with 5 page faults, we're gonna get 14 and 13. So, you see what we're doing here now? We are slowly adding more page frames to our program here. Because there is this idea in memory where you have this intuition where here's the thing. If you don't have enough page frames, then your program is likely going to page out a page that it's going to need to page in immediately again. So to avoid that, we need to give it extra page frames to avoid that extra paging. So the idea is this. The fewer page frames we have, the more page faults we get. So conversely, the more page frames we have, the fewer page faults we get. I got 14 and 13 here. Okay, let's make sure that it really is 14 and 13. Yep, 14 and 13. Let me just compare it 4 to 5 again. Okay, that was 14 and 13. 7 page frames yields 14 and 13 again. Eight. 12 and 12. Nine page frames yields 12 and 11. Ten page frames yields 10 and 10. Oh, but wait, we already got 10 and 10 when we did 20 page frames. So, here's the thing. You don't need to fill out the whole table, because once you get 10 and 10, then at that point, we have enough page frames to hold every page the program will ever need. So at that point, we can just stop filling out the table, because filling out these columns here is redundant. So you only have to go as far. You only need to keep going until you reach a column that has the same values as this one. So you don't have to fill these in. And even if you did, it's going to be these values anyway, at least for this example. So I want you, for part 4, fill out this table. So, slowly increase the number of page frames by 1 each time, recording the number of page faults that LRU and FIFO produce. What you're trying to do is this. Did you get something weird? There is something weird that can happen. So the intuition is this: the more page faults the more page frames you have, the fewer page faults you get. But there is something weird that can happen where, with FIFO, specifically, if you increase the number of page frames, you don't always get a decrease in the number of page faults. This is something called Bellidy's anomaly. And it's through the discovery of this anomaly that led to the development of what we now call optimal page replacement. Because Bellidy's anomaly is this weird thing that only happens with FIFO, in that, as I said, an increase in the number of page frames may not always lead to a decrease in the number of page faults, and in some cases it can make it even worse. So that is Bellidy's anomaly. Did you ever observe Bellidy's anomaly in this example here, where the page fault rate went down and at some point went up? In this example, it did not, because the page fault rate did go down, even though at some points it stayed constant. And that's because for some pages we were just accessing the same page twice. So, see whether you got Bellidy's anomaly. That's the final 10 points on your assignment. So, that is your whole assignment right there. Screenshot of your RNG output for part 0, screenshot of your program's output for FIFO and the sequence of page numbers produced. That's part 1. Part 2 is screenshot of your program's output for LRU and the sequence of page numbers produced. Part 3 is manually compute and optionally verify the number of page faults for both sequences for part 1 and part 2 for optimal page replacement. And then optimal page replacement could yield a better result. Part 4 is to populate the table, and the other 20 points is the source code of your program. And finally, 10 points for answering the question, did you get Bellidy's anomaly or what? Okay, so that's the last. That is your lab. That's gonna double as your final. So, we really. So, the latter half of the term was basically all, for the most part, all about memory. Yeah. Okay. The latter half of the semester was like all about memory. We were mainly talking about that. I really wanted to talk about other topics as well, such as security and protection. I didn't get a chance to do that. I wanted to talk about multi-core CPUs. I didn't get a chance to do that. Maybe that's going to be something for 4610 though. So I am going to put out an extra video where I do my best to at least give you an idea of what those missing topics are. I hope you had a great time at least learning about these various different operating systems concepts, because we are surrounded by computers like every waking moment of our day and night, 24/7, 365. We're just surrounded by computers. So, as computer scientists, it's a really good idea, and like, it's a good idea to like, even if computer science is just a minor for you, then hopefully this gave you a really good appreciation about the technology that we have today and how it came to be. Especially the part where I talked about the history of computing, how there were like 4, or depending on how you count it, 5 distinct generations of computers. Starting with vacuum tubes and then working our way up to the microprocessor and then the personal computer. Who knows what the 6th generation is going to be looking like, but it's probably going to be AI assisted. It's probably going to be in part AI assisted. Well, we're going to have to see what happens in the next few decades. It's going to be a wild time, whether we like it or not. What with Moore's Law and GPUs and AI coming of age, despite all the AI winters that have happened in the past. Anyway, hopefully you've learned quite a bit, and hopefully I've made the class like legitimately enjoyable for you to learn about. So, with that, I'm going to upload this now, and yeah, that's the end of class. And with that, I'd like to congratulate you for making it to the end. You did good. And with that, I'll see you later.